Okay, let's look at another system, and we're doing some loop shaping on this. Let's look at a second order system, and let's look at an open loop transfer function of 100 s plus 30, similar to what we had last time, but let's square it this time. And so we end up with a couple of poles there at 30, and making it a second order system. And so we know from our experience that we're going to introduce some oscillation with this as we increase the gain on this system. But let's see what we can do with it as far as a Bode loop shaping is concerned. So let's calculate the DC, which is going to be 100 over 30 squared, which is going to be 0.111, and run the dB is going to be 20 log 0.111, which is going to be minus 19. Okay, and so looking at this, 10 to the 0, 10 to the 1, 10 to the 2, 10 to the 3, 10 to the 4. All right, and let's go 0, 20, minus 20, minus 40. And so we're somewhere almost to the minus 20. So right in here as our starting point. We have no free S's, so we're going to start with a horizontal line through here. And we're going to go to 30, which is right about here. And at 30, we've got two poles in here. And so we're going to break twice, two single poles break twice. So we're going to end up with a minus 40 change in slope. So one here to there. So we're going to end up something like this. This being a minus 40 dB per decade slope. And we end up with a phase 0, minus 90, minus 180, 0 out to 30, and then minus 180 from there on over. Okay, so that's going to make this look something like that. All right, so we look at this, and of course, the first thing we could do is just try a proportional gain. If we have minimum requirements on this, minimum specs, we could close the loop, increase the gain, and hopefully get within our requirements for the system. And we could just by increasing the gain, of course, we're going to go up and down with this, and so we could shove it up. But we also know that what's going to happen from our root locus is that we're going to create a more unstable system, and we probably have some high frequency stuff out there that's going to be problematic at some point. Let me bounce over here to a SISO tool. We've got I've got our system in here in as our system, and so this is the root locus, and this is for a gain of 1 for our system. And we see we've got a first order-ish type response. We're just a little bit into the complex plane, probably getting a little bit of overshoot, not showing up too much there. As we start increasing the gain, start lifting this up, of course we start moving those poles further into the complex plane and getting a little bit more overshoot, and we're quickening it up, getting it faster, but very quickly we start picking up some overshoot, some pretty significant overshoot. Now we can back this down a little bit, and depending on the specs for our system, we may be able to live with this. We've got a little bit of overshoot. We've got a steady state error in here, fairly significant steady state error. And if we're going for a regulator type controller, we could crank this on up and tolerate the oscillation at the beginning, and knowing that it was going to settle out and we were going to reach a steady state value and have a minimal steady state value with this kind of gain. Okay, so on a motion control kind of application, this would probably not be acceptable because your device would be moving all around where you didn't want it. But in a regulator type application, we may be able to live with this. But let's look at something a little bit different. Let's try to do a little bit of shaping with this with a PID controller. Let's say in this case we wanted to improve speed. Okay, so when we say that, we're thinking about PID controllers, we're thinking a PD controller. Okay, and PD is a KS plus Z. We're going to add a Z to the system, and that's what we need in this system, because what we want to do is shift this back over here to a minus 20 dB per decade to improve stability across our crossover. And so we're going to need a 0 there to do that in order to improve the situation. Okay, so now the question becomes, where do we put that 0? And again, there's a couple ways that I would approach this problem. One is from a high frequency standpoint. What's our high frequency? Or what is our time domain specs? In this time I'm going to give us a settling time of, let's say, 0.003 seconds. See if we can meet that. And so remember, settling time is equal to 1 over zeta omega n, and I'm sorry, 4 over zeta omega n. And so if we solve this, 0.003, and we say let's minimize the overshoot, so let's set zeta equal 1 and solve that for omega n. We get an omega n of about approximately 1200. Okay, and so with that we have a place to set our crossover frequency. We would want our crossover frequency in here about 1200, okay, as our omega n. Okay, that means we're going to back up 1 decade from that and set our 0 at that back here. So our 0 would set back here at 0 would be equal to minus 120 in there, and that would have then we would end up with our negative 20 dB per decade for a decade before and a decade after our crossover frequency. And so we'd set that back in here at 120, almost got it there, back in here, and so we would end up like this. And then we would raise this whole thing by increasing the gain up to where our crossover frequency, our new Bode, modified Bode, would end up with the crossover frequency. So let's try that and see what we end up with that. Okay, so let's pop over here to MATLAB. Let's come in here and grab a 0 and drop it in here. Okay, and that looks familiar from our on our root locus. Let me get to our controller. I'm sorry, I chose the wrong one. Let's get to our controller, and let's put this in at 120, or 0 in at 120, and then let's lift this up to having a frequency. Remember, our phase margin is calculated or found at our crossover, so we're going to lift this up to where our crossover frequency is at 1200. That's can be easier to do over here. I'll increase the gain. To 1200. Oh. It's tedious. Okay, close enough. 1250. And we didn't quite meet our time domain spec, but remember, the time domain specs were developed on a second order system. Now, while we had a second order system, we also introduced a zero. And so we've changed the system. It is no longer a second order system. It's different. It's a second order with a modified input. And so it's not going to be exactly, but it'll get you in the ballpark, give you some place to shoot for. But we've got a nice response in here. It's very fast. It doesn't oscillate a lot. We get a little bit of overshoot, and then it settles down and does a pretty good job of it. Okay, so that would be a pretty nice controller for this. Now, we could go on and go for broke on this and implement a PID. Now, if we added to the specs, in addition to improving speed, what if we also added to that minimize steady state error? Okay, which means we're going to want to put a free integrator in there, which means we're going to add a going to be talking about an integrator term. But if we're improving speed and minimizing steady state error, what we're going to be implementing at that point is a full PID. And if you remember, PID is going to be a gain, S plus Z1, S plus Z2, and a free integrator. Okay, so we've got a gain, 2 zeros, and a free integrator. Now, if we think about that in terms of what we're doing with our loop shaping, what we're going to end up doing is we're going to have an initial slope in here of 20 dB per decade from our free integrator. We're going to come and we're going to hit these two poles here at 30, which is going to kick us down. Now we're going to be heading down at minus 60 dB per decade. Minus 60. So we're really going to be zooming down. But along here at the minus 120, we kick in 2 zeros, okay, and then that kicks us back up to a minus 20 dB per decade across here. So then we slide the whole thing up to where we have our zero crossing at our omega n, and we would implement a full PID at that point. Okay, so again, what we're doing is we're getting it up here, down here, and 20 dB per decade across our crossover frequency. Okay, so let's see if we can implement that with our system in here. So this time I'm going to pull up my controller. Maybe try that again. There we go. And I'm going to just go ahead and add some poles and zeros. So I'm going to add a pole at, and I'm going to put this at the origin. That's going to be my free integrator. And I'm going to add a zero, a real zero, and I'm going to put that at minus 120. Okay, and so now I've implemented my two, oh, no, sorry, got that one wrong. Zero, changed the wrong one. I want my zero at minus 120. Okay, there we go. Now I've implemented a full PID on this, and you can see we've got this initial slope in here of minus 20 dB per decade, which is going to give me my steady state error. I've got a minus 20 dB per decade across here, which I'm going to slide up across my my crossover frequency. And let's see if we can do this by changing the gain over here. Now you notice when I do this, changing the gain on my root locus, I'm also changing the gain on my Bodhi. So I'm taking it higher. Okay, and so it's at 690. We want to go ahead and take it on up. Let's see if I can take it on up. 800. There we go. Right in there. Okay, close enough. All right. So now what I've accomplished in this is I've minimized my steady state error. My steady state error should be a 0 on there. I've got a good time in here. I didn't quite hit my 0.003, but now I've got something way different than the second order. But I'm in there close. I've got a little bit of overshoot in here, but I've got a good, nice controller, good stable. You look in your phase margin at 82 degrees. We have an infinite gain margin. So I've got a nice stable system in here that I've implemented and I designed for this system. Okay.